Okay, we will jump into a new chapter today, and probably to the rest of the semester, we are going to need the information that we start today. Of course, we are going to need the linear and time invariant system properties like impulse responses and the concept of convolution. That's critical, but a methodology to look at the signals and the systems in a different way will help us solve a lot of problems. And despite it requires some new information, some new formulas like what is a Fourier transform that we're talking about. But once you have those tools, necessary tools, you will be able to look at the problems in a whole new perspective. In fact, when I first learned about the concept of Fourier and the transform, I found it really fascinating because for the time being, we always look at the functions on an axis that we have been intuitively using all the time since our primary school days. We write functions f of t. And that t over there inside the parentheses corresponds to the free variable that we have. I never thought that another free variable could also replace t in a different perspective to look at the signals. And that is the frequency scale. How can a signal have a new representation on a different axis? And that axis is not time, but it is f, frequency. What does that mean? So the name of the new chapter is something more specific. Let me write it first. It is continuous time Fourier series that I'm talking about. But the concept that I'm trying to explain is not for the continuous time only. It is also valid for discrete time. And it's not only for Fourier series, but it's valid for all types of Fourier transforms that can be thought of. And that is, instead of the time axis that we draw, I'm going to erase it and I'm going to put a frequency over it. And can it represent signals? Can we still represent signals here? And the answer to this question is a quite clear yes. Let's think of this signal. And here it is, let's say, 5. And the value is, let's say, 2. By the way, this is a new representation of the signal which was previously expressed in terms of time variations. So the question is, what is the time corresponding signal? The methodology that I'm going to use will be like this: x of f. But in order to differentiate between x of t, which is usually indicated with a lowercase letter, in the Fourier or the frequency domain, I'm going to represent it in uppercase letters, capital letters. Capital X of f is this. If I say it like this, what does it correspond to? It corresponds to the so-called, or this thing corresponds to the so-called harmonic. It's a harmonic. It's an oscillation. It's a periodic signal with a frequency of 5. Let's only think of cosines for the time being. It's not like that. It's a little bit different, but to motivate things, let's start with a simpler example. Let's consider only cosine harmonics for the time being. If this harmonic is a cosine with frequency 5, and a magnitude of 2, then the corresponding time domain signal would be x of t is equal to 2 times cosine 2 pi ft. F The frequency, what is that? 5 t, or it is 2 times cosine 10 pi t in short. And in time domain, if you try to draw this, what would it look like? It would look like, on the t-axis, a cosine signal like this, extending to both sides. And this point is 2, this point is minus 2. And how about the period? The period is here, that it repeats, it makes one full cycle. What's the period? It is 1/5 seconds. What's 1/5 seconds? 200 milliseconds, let's say. Let's write it in terms of milliseconds. Then this would be 200. Right? This would be 100. This would be 50. Like this. So, my new representation, or my new way of looking at the signal, is a transformation from here to here. Instead of drawing the cosine signal like this, I will indicate it on the frequency axis and put one sample, because it has only one harmonic. Of course, life is not as easy as this example. In many cases, the signal at the bottom figure will have more harmonics. It will be a more general way of looking at a signal. So it will have not a single harmonic like at the top. Instead, it may have something more. For example, it may have another harmonic at 8. It may have another harmonic at 10 with a -1. Notice that the scales could be just any real numbers for this case. As a matter of fact, they don't even need to be real numbers. They could even be complex numbers, because we don't restrict our signals to be real valued or complex valued. They can be just anything. So if it contains like that 3 harmonics, then it would be a combination of 3 sinusoids, 3 cosines for this case. One of them will be at 5 hertz, the other one will be at 8, and the other one will be at 10. So that combination, that new axis, is called the spectral axis. It's not the time axis anymore. It's the frequency information that it carries. And frequency and spectrum are two acronymous names for the same thing. Okay, they correspond to the same thing, in other words, spectrum or frequency. And the methodology to represent these things, or any kind of a signal on the frequency axis, is called a Fourier transform, due to the scientist Jean-Baptiste Fourier, a French scientist who invented the concept that any kind of a periodic signal, a cosine by itself is a periodic signal, but there are other non-sinusoidal periodic signals as well, right? For example, a triangular waveform or a rectangular pulse. It's also periodic. He claimed that, and he has also proven any such periodic signal can be represented as a combination of harmonics, and they can be represented in the top figure. But since harmonics are sinusoids, smooth oscillations, he had a lot of disagreement from other scientists. He tried to publish his observation, but the publication was clearly rejected because no one believed. How can it be possible that a rectangular waveform can be obtained by adding a lot of smooth sinusoids at different frequencies and different magnitudes and different phases as well. We didn't mention about the phase yet. The phase will come from complex magnitudes in the harmonics. How can it be possible? It's hard to believe, really. I mean, it's quite discontinuous. It's not differentiable, at least. It is continuous, but quite non-differentiable. So, addition of smooth signals will eventually yield something smooth, intuitively. So, by adding lots of sinusoids, how can we get some sharp shapes? It looks impossible, but it is. Since it looks impossible intuitively, no one believed in him, so his publications were rejected by a lot of other famous scientists like Laplace and Lagrange and several such scientists of the same era. As a matter of fact, Fourier was not as famous as those other guys. Jean-Baptiste Fourier was a moderate scientist. The others were popular, well-known, well-established scientists, and well-established scientists did not believe him. But later on, after solidly proving the convergence of that, I mean, by proving that Fourier series summation is an adequate representation, they had to agree that it's correct. And they not only agreed, for example, Laplace also extended the Fourier transform to the Laplace transform. In differential equations, have you seen this S variable, S? Okay, that S variable is an extension of the frequency. It's an extension of the Fourier transform, also known as the Laplace transform. You already know the Laplace transform. But it is something that first Laplace disagreed, and then agreed, and then extended. So how can this be possible, and how will this new representation help us? The new representation shows us the harmonics, and those harmonics will visualize a different way of looking at the same signal for signal analysis. I'm sure you must have seen, nowadays there is digital music, and in the analog times, we used to have equalizers and Wu meters, the so-called very 80s sort of things I'm talking about, okay? Some ancient stuff. A Wu meter was something like this. It was showing the frequency of the audio changing in time. So, for example, if there is some low frequency content, the left-hand sided LEDs were lighting. If there is high frequency, then the right-hand sided LEDs were lighting. So it was just a visualization. So it was like this, boops, boops, okay? That Wu meter thing. And an equalizer was a tool which is deliberately designed to improve some of the harmonics, some of the spectral contents, the high frequencies, the low frequencies, or the mid-ranges, to suppress them, to attenuate them, or to amplify them. Okay. So those things, the horizontal axis on both of these things were frequency axis. And what you are doing is a filtering on the frequency axis. You are increasing high frequencies, low frequencies. So you want to visualize or see the frequency content of your signal. If, for example, it's it may be a white noise, which means there is no specific harmonic. All the harmonics have the same amount of information. That is called a white noise for some reason that I will explain. So it's flat on the frequency axis. The sunlight is an example to that. It contains all the frequency information in the visible range from red to blue. And the overall color is white. That's why it's called a white noise. It means all the frequency harmonics are equal. That is usually corresponding to a noise. It doesn't carry any information. But for example, there are deep space antennas which are gathering some information from the outer space. And in most cases, they just observe white noise with no specific harmonic. It's just white noise. But sometimes they receive a Fourier transform which doesn't look like this in the important range between two frequencies. Usually it's like this, the Fourier transform. But sometimes they observe something like this. Now what is that? What does that mean? It means that there is an oscillatory signal, there is a harmonic at this particular frequency of F1, which must appear due to something rotating or some deliberate signal that has been transmitted towards Earth by some space aliens or whatever. It may mean something. So we need to look at things like that. We need to look at the harmonics for the information. We all use, for example, the MPEG audio layer 3, also known as MP3 music. It is a compression standard which reduces the amount of file to a smaller file size. It's not like the lossless WAV file. It's not the WAV file that is inserted into this so-called MP3. For those of you who could think of audio compression as a project, here's the deal. An MP3 standard is like this. It quantizes you have to quantize, level the information to reduce the number of bits. Normally it was like 16 bits for every sample. But if you use 8 bits for every sample, then it will be a worse music because the quantization levels would be more coarse. But it will be smaller. What MP3 does is it converts the signal into frequency domain first and looks at the harmonics, contents. These strong harmonics are quantized using some bits, but the lower magnitude harmonics are quantized using less number of bits. Therefore, most of the bits are used for the reasonable component only, and for the useless components that we cannot hear or anything, they use less number of quantization bits, and the overall number of bits is reduced. It is less than the time domain representation. And every player, MP3 player, applies an inverse Fourier transform to convert it to time first, and then play it on the loudspeaker or your earphones. It's constant inverse Fourier transformation, that player. So it is also useful for compression. It is also useful for analysis as well. It's a brilliant thing. Yeah. Summation of sinusoids. Different Yes, we will see that. That's a good question. I mean, it's not a sine plus cosine or anything. It is a cosine with different phases. Because a different phase, cosine is a sine anyway. But it's not necessarily only sine or cosine. Arbitrary phases, delays, is also possible. We will see that. For example, wouldn't it be a good idea to look at the Fourier transform of the stock market values? The stock market values are increasing, decreasing. There may be an increasing trend or a decreasing trend, but they are locally increasing and decreasing. Now, let's assume that you take the Fourier transform of it and you see a huge harmonic with a frequency corresponding to a period of, let's say, 8 days. 8 days. Then what does it mean? It means that in 8 days it is increasing and decreasing. So if you can somehow catch the decreasing and increasing points, if you can catch the phase by looking at the Fourier transform, then every 8 days you buy at the minimum of the oscillation and you sell at the maximum. And then you buy at the minimum and then you sell at the maximum. Every 8 days. You can earn money. If only the stock market could have a reasonable Fourier transform. Trust me, it doesn't have it. Is there a question? Ah, you were doing something. Okay, sorry. But as you see, you may look at the information embedded inside noise, which you cannot visually see when you look at the time variation of the signal. But when you take the Fourier transform, you can see something over there. Okay. So today we will start with the first strategy to transform signals, periodic signals, and continuous time periodic signals onto the frequency axis. We will learn how to do that. And that is called the continuous time Fourier series. This term series, not the transform, but the series, comes from the fact that the input signal is periodic. If this input signal is periodic, we have Fourier series. If it is non-periodic or for more general, broad class of signals, we have a Fourier transform, which is quite similar. It's more or less the same thing, but we will start with the series. And the sinusoid that we will use will not be cosine, it will be the complex sinusoid. And the complex sinusoid that we are going to use is e to the j omega t. E to the j omega t, this omega is 2 pi f. But our book prefers to use omega as the frequency instead of f. F is more intuitive, but for the rest of the compatibility issues, we will stick with the omega representation. Omega is 2 pi f. So the new frequency is omega, and the unit for the frequency omega is not 1 over seconds. It will be radians per seconds. 1 over seconds is hertz. 2 pi times hertz is radians per second. And from the Euler's theorem, this is cosine omega t plus j times sine omega t. Alright? So it has a real part and a complex part. Both of them are sinusoids, and in overall, that corresponds to a complex sinusoid. So the representation will be the omega axis, and the magnitudes will correspond to the magnitude of this thing. A times e to the j omega t, for example. So A will be the magnitude at the frequency omega. And this A could also be complex, by the way. If it is also complex, having both real and complex, real and imaginary parts, you have to multiply the real and imaginary using the cross multiplications for expanding into cosines and sines. You don't need to expand them in general. Why do we use complex sinusoid for linear and time invariant systems, and how come it will help us is the second question now. That's a magical thing. If you have e to the j omega t, regardless of the omega, whatever this omega may be, it's just a free frequency. But for a fixed frequency, this is a sinusoid. It's a complex sinusoid. Suppose that this sinusoid goes into a linear and time invariant system with impulse response h of t. What will be the output is the question. And I claim that the output is the same. Complex sinusoid scaled by a factor. It is just scaled, but it goes out the same. If something goes into you must have seen linear algebra. Do you remember anything like this? If I have a matrix, let's say T matrix, and a vector X that can be multiplied, a matrix vector multiplication, and this multiplication will give you the same X scaled by a scalar, a complex or a real scalar. So the vector comes into the system of T, and the output is the same vector X. What is this vector? Do we have a specific name for such vectors? It's an eigenvector, right? And then lambda would correspond to the eigenvalue of the system T. Now, if you compare the two terms, you will see that this complex exponential e to the j omega t now has a name called the eigensignal. Complex exponentials are eigensignals of LTI systems. When they come into the system, they go out of the system only scaled, without changing the behavior. It will be still the same. But what is this A is something important, of course. For that we need to apply the convolution. Let's try to convolve e to the j omega t with h of t. Let's make this convolution. I don't remember which one I should put first. Let me put h of tau and x of t minus tau, which is e to the j omega t minus tau d tau. This is the convolution. And then from minus infinity to infinity h of tau e to the j omega t times e to the minus j omega tau d tau. Okay, I expanded the exponents. And this thing, e to the j omega t here, has nothing to do with the integration tau. So we don't need to keep it inside the integral. We can take it out. Times the integral will become from minus infinity to infinity h of tau e to the minus j omega tau d tau. Now previously I said that the output should be a times e to the j omega t. Now do you all agree that this is equal to a times e to the j omega t, where a is this? It looks too complicated, a then, but it is an a, and it is not a time function. There is no t inside it. There is no tau inside it either, but there is an omega inside that. When you take the integral, when you take that integral, omega will still appear in the expression. So this is something in terms of omega. It is not a, but it is a of omega sort of thing. We are going to express it like this for a reason, of course. H of omega, I will say. So what have we observed? This changes, of course, with different omega. But when you take a look at the top expression, I'm going to write it like this: h of omega times e to the j omega t. The shape of e to the j omega t doesn't change. It is still there, but it is scaled by a constant. But that constant, the value of that constant, however, depends on the frequency. So if this omega is, for example, x radians per second, then h of omega will have a value. If it is y radians per second, then h of omega will have a different value. It is just like this eigenvalue, eigenvector expression in the second line. For every eigenvector, we have a different eigenvalue. Every eigenvector corresponds to the corresponding eigenvalue. So these eigenvalues, h omegas, will change by omega. But that is the behavior of the system. It's the response of the system to certain frequencies. Like what? Let's assume that omega is equal to 0. Let's look at the top illustration. Omega is equal to 0 is what? What kind of a periodic signal is that? It's a constant signal. E to the 0 is 1. So we input 1. It's the DC. Right? 0 frequency DC. Then the output will be h of 0 times 1. That h of 0 will correspond to the DC passing property of your system. How does it pass DC? By an amount of h0. If omega is increased a little bit more, let's say 5 pi radians per second, then the corresponding h of omega will have a different value. Let me draw some h of omegas. Yeah.
Hocam bu en son yaptığımız şey birlikte olan şey aslında sistemin o etkisinin frekanstaki şey gibi.
Yes, it is also known as the frequency response, not the impulse response. Impulse response was h of t. This is called the frequency response. Exactly. So it's a very nice name to use. How does it respond to different frequency inputs? Now let me give you some examples of frequency responses of h of omega. These h of omega figures in questions, they must be given to you. You must have them to solve questions. For instance, let's think of this. From minus w to w, this is h of omega on the axis of omega. This is a frequency response of a system. Can you name this system? Can you give a name to this? It's a filter. It is filtering some frequencies by passing or by stopping them. This is, does it look like a band pass? Yes, of course, everything is a band pass, but this has a more specific name. Because the band is only low frequencies, starting from 0 to W only. So the low frequencies are enabled. They can pass. So this is a low pass filter. How does it behave? What do we mean by a low pass filter? A low pass filter behaves like this. We will learn the methodology to find the Fourier series coefficients and label them on the frequency axis for our periodic signals. We didn't do that yet, but we will do that. Let's draw our Fourier series. And the Fourier series will be like capital X of omega. Previously I wrote it like capital X of f, but I'm not going to use f anymore. For compatibility, the frequency will always be on the axis of omega. Suppose that our signal has a DC component with some value and some frequency harmonics. For real signals, the harmonics will correspond to the conjugate pairs, so they will have the same magnitude. We will see why, but this is just an example anyway. Some other high frequency harmonics like this. Okay, so suppose these are the Fourier series coefficients or the harmonics of my input. The question is this: when this periodic signal at the bottom passes through a system whose spectral response or the frequency response is like that, what is the output? At the output, these components will not pass because they will be at a frequency higher than the available maximum frequency of W, visually at least. The others will be inside, and as you see, every harmonic is multiplied by the corresponding h of omega because of this formula. So if you have a harmonic at a frequency W with a magnitude, that magnitude is whatever it is, let's call it C. So C times e to the j omega t will go into the system, and the output will be h of omega times C times e to the j omega t. But h of omega for high frequencies higher than W is 0. So the output of C times e to the j omega t will be 0 times C times e to the j omega t at that frequency. So we are multiplying these two shapes. This thing, this component will be multiplied by something constant. Let's assume that constant thing is 1 for convenience. And then this one will not change. This one will not change. This one will not change. But the others will be multiplied by 0, so they will be eliminated. What is the overall effect? The overall effect is a low pass behavior because the high frequency harmonics are eliminated. The high frequency oscillations are gone. Only lower frequencies pass. And we will call this a low pass filter. Of course, you can think of any other types of filters, like your friend has suggested. For example, let's try a band pass filter. A band pass filter usually has a starting and an ending frequency of W1 and W2 with its reciprocal minus W1 and minus W2. Why do we have it? Because, as I say, for real signals or for real filters again, these two right-hand side and left-hand side shapes would correspond to the conjugates. So the magnitudes will be the same at the right-hand side and the left-hand side. So if we input the same x of omega at the top from this bandpass filter, probably this time these components or that component, it's a single component, will pass because it fits inside the frequency range, frequency band. The others will not fit into the frequency band, so they will be attenuated down to 0. This will only pass a band. Those Wu meters things work as follows. They have a lot of bandpass filters and they pass specific frequency components, lowest frequency, something higher frequency, something higher, and the highest visible frequency. They pass through multiple channels, and at the end of those bandpass filters, they measure the magnitude. If the magnitude is this much, then they generate this much Wu meter output of LEDs. If it is low, if the bandpass output is low, then it means the harmonic corresponding to that bandpass range is not very strong. So it will be a lower LED marking. And the equalizers are variable bandpass filters corresponding to separate bands. You increase the amplification or you decrease down to the attenuation of those filters. They are adjustable, tunable filters in other words. So if ever we could find a methodology to extract these harmonics from a periodic signal, and if ever I give you the system, it may be a bandpass filter, a low-pass filter, it may be a high-pass filter. What's a high-pass filter? The high-pass filters are usually like this. They stop the low frequency within some range from minus W to plus W, and then afterwards on the frequency axis it passes everything. So this is a high-pass filter, for example. Can we think of other passing filters? Band reject, yes, or band stop. It would probably be like this. It passes the low frequencies, it passes the high frequencies, but it doesn't pass, for example, between minus W1, plus W1 and W2 and minus W1 and minus W2. Only those certain harmonics are deliberately suppressed. Now, for example, if you work for audio signals, when acquiring audio in a laboratory environment, you notice that there's a strong 50 Hertz noise coming from the city electricity. Okay, the electricity is at 50 Hertz, sort of a low frequency thing. It may be a good idea before trying to record anything to first suppress that 50 Hertz and don't pass it. But it must be a very narrow band stop filter. Their design of such filters it's a circuits and electronics issue. So very narrowly you suppress 50 Hertz, then you will not notice that 50 Hertz electricity noise. for example. It may also be useful. These are very standard filters, but of course we may have other filter types, quite arbitrary filters as well. For example, what is this? It is again sort of a low pass filter because it doesn't pass high frequencies, but in the low range it is distorting the signal a little bit. The lower the frequency is, it means it's nearer to the center, then it is amplified even more. So it is somehow distorting. What you really need to do is, for those, you need to find the harmonics of your signal, and then at their corresponding places you must multiply with the corresponding filter value. So this harmonic, for example, will pass like this. It will be multiplied with this value. This harmonic will be multiplied with this value. This DC harmonic will be multiplied with the sample value, etc. That's how you filter, pass your periodic signal, by finding the harmonics and multiplying with h of omega. It may be even more complicated shapes, but that shape must be given to you in order for you to solve the question. So what are these harmonics? That is our next question now. We will try to see from simple examples first, and then we will generalize to a formula, and using that formula you should be able to find the harmonics of any kind of a periodic signal. So what could that be? For example, x of t is equal to 3 cosine 2 pi, let me not write 2 pi, but let me write 8 pi t. The question is this. It looks like a single harmonic, by the way, but remember that by saying harmonics, I'm asking for the complex exponentials and the coefficients of those complex exponentials. X of t is 3 times cosine 8 pi t. You just need to expand it using the Euler's formula. And what is that? What does that say? It is 3 times 1 over 2 e to the j 8 pi t plus 1 over 2 e to the minus j 8 pi t. Do you remember this formula? Yeah. This is the expansion of a cosine. The expansion of a sine is a little bit more complicated, or it's not very complicated, but it's different. It has a minus sign in between. That is the difference. And it's not 1 over 2, but it would be 1 over 2j for a sine. So this is cosine anyway. So how many components, how many harmonics do we have now? We have clearly 2 different harmonics. 3 over 2 e to the j 2 pi 4 times t. I'm going to write it like this, plus 3 over 2 e to the j 2 pi minus 4 times t is what I'm going to write. So now we have 2 harmonics. These 2 harmonics have the same magnitude. The magnitudes are this. But where are they? What are the frequencies of these harmonics? The frequency of the first harmonic is 4 Hertz. For the other one, the second harmonic is minus 4 Hertz. Okay? Or if you think of it in omega, the first one is 8 pi, the second one is minus 8 pi. So let's draw these things on the axis of omega. And the magnitudes will be 3 over 2 and again 3 over 2 at eight pi and minus 8 pi. So these are the harmonics that you must put. And if you ever have a filter of any shape, let me draw the filter shape with a red, like this. The corresponding value of that filter will amplify or attenuate. It must scale, in other words. This is 3 over 2. If this is h of omega. Yeah? Now, if you have a single harmonic, or if you have a fundamental period, then the numbering of the harmonics is something quite critical. So the next issue is numbering of the harmonics, or also known as the Fourier series coefficients. How do we number them? Let's go back to our example. If you have a single sinusoid, then the harmonics are numbered as follows. It also corresponds to the period of your periodic signal. What's the period or what's the frequency of the overall thing? The frequency is 8 pi and minus 8 pi. That is also known as the fundamental frequency. There is no other frequency here, of course, but that is the fundamental frequency. The coefficient of the fundamental frequency must be labeled as A or C. Which one should we use in the book? Well, let's use A1. So that is the Fourier series coefficient of the fundamental frequency. The negative of that frequency would correspond to A minus 1. So this is the numbering. If there is a zero DC coefficient, that coefficient must be represented as A0. Okay? There is no DC coefficient here. So this is A1 and A minus 1. But that was an easy example. Now my next signal is like this. Cosine 8 pi t plus 2 sine 6 pi t. Again, using the Euler's formula, we can of course expand this thing into how many components now? The cosine will have 2, the sine will have 2, a total of 4 components. And let's write them. 1 over 2 e to the j 8 pi t plus 1 over 2 e to the minus j 8 pi t plus 1 over 2j times 2, it is 1 over j e to the j 6 pi t minus 1 over j e to the minus j 6 pi t. For the sine, there is a minus sign in between the two. And instead of 1 over 2, we have 1 over 2j. That is the difference for Euler's expansion of sine. So these are the components. But what is the numbering? We can clearly insert them on the omega axis. There is no problem. At 8 pi, we will put a 1 over 2. At minus 8 pi, we will put a 1 over 2. At 6 pi, which is a lower frequency, we will put a 1 over j or a minus j. A minus j, how do we put them? Don't worry about those things. Just put something and indicate its value to be minus j. And at minus 6 pi, there will be a plus j. So these are our harmonics. Minus j at 6 pi, At 8 pi I have a 1 over 2. At minus 6 pi I have a plus j. And a 1 over 2 at minus 8 pi. If you're uncomfortable with the minus j representation, it must be the negative of the j. Just put it downwards if you wish. But it's complex anyway, so just indicate the magnitude. Now the question is this. How do we number these? Is this A1? And then this would be minus A minus 1. A minus 1. And then is this A2 and this is A minus 2? Unfortunately not. Now this is the trouble that we have to deal with. This is not A1 because that 1 index should correspond to the fundamental frequency. You must ask you this question. What is the fundamental... oops, sorry. Come on. What is the fundamental frequency of this goddamn signal? Whatever that fundamental frequency is, all the frequencies of the harmonics must be integer multiples of the fundamental frequency. Integer multiples. As you see, if fundamental frequency is 6 pi, then 8 pi is not an integer multiple of that. So 6 pi is not the fundamental frequency. You can also ask you the reverse question. What is the period of that signal at the top? Or what is the frequency of that signal, which is the inverse of that period? If you try to draw this, you will see that the frequency is not 6 pi. The frequency is not 8 pi. What is the frequency? A frequency is something that this signal segment identically repeats itself. Not approximately. It must be precisely repeating itself. When does it precisely repeat itself? No. It has a finite frequency. This is a periodic signal. Because 6 pi and 8 pi have a common divisor, 2. So, as a matter of fact, the frequency, the fundamental frequency, is the common factor of 6 pi and 8 pi, which is 2 pi, I guess. 6 pi is 3 times 2 pi, and 8 pi is 4 times 2 pi. So, the fundamental frequency here is 2 pi, and all of the harmonics are integer multiples of this. So this is not A1 then. I must erase them. What is it? It is A3, 3 times the fundamental, and this is A4, and therefore this is A minus 3 and this is A minus 4. We don't have a harmonic in the fundamental frequency. The fundamental frequency is 2 pi, but we don't have a harmonic there. The first harmonic appears at 3 times the fundamental frequency, and the next harmonic appears at 4 times the fundamental frequency. If you start combining multiples of sinusoids, then you must be careful about that, because you must eventually express your x of t like this. K from minus infinity to infinity, there may be infinitely many harmonics. AK times e to the j times 2 pi times k times the fundamental frequency f0 times t. F0 is the fundamental frequency in hertz. Let me write the same in omega notation, which will be more useful for you. K from minus infinity to infinity, ak times e to the j times k times omega 0 t. So this omega 0 is the fundamental frequency, and every harmonic must have a frequency in integer k times omega 0. So your duty is to first determine omega 0, and then what is this frequency in terms of that? That is k times omega 0. And this is a necessary condition, and it makes the life of Jean-Baptiste Fourier even worse, because he not only claims that it's a combination of harmonics, but he also claims that it's a combination of harmonics at integer multiples of the fundamental frequency. This k is not arbitrary, they are all integers. So it's even more difficult to prove this, but that's the case. By the way, if the two components here for the cosine and sine, let me ask you something, and I will ask you to find the Fourier series coefficients, sort of. Cosine 10t plus cosine 8 pi t. What are the Fourier series coefficients? And when I ask this, I would expect this result, this answer from you. This is not a periodic signal, because there is no fundamental period. Is there a fundamental period or a fundamental frequency? The fundamental frequency is 0, the fundamental period is infinity. This is not periodic. You cannot find omega 0. And since you cannot find omega 0, you shouldn't talk about the Fourier series coefficients and all those things. And you should quit answering immediately, saying that this is not periodic. That would be the correct answer. We will continue with these issues. So let's stop at this point.